Uh, Hello. So today let's begin with advanced approach to multiview stereo. So in previous class we studied basic concept of multiview stereo. What is the multiview stereo and what is difference between structure from motion and multiview stereo, and some simple approach to multiview stereo. Today we will study two types of advanced approaches to multiview stereo, and this shows advanced approach to multiview stereo. The first one is plane sweep stereo. In one sentence, it places several flat planes parallel to the camera image at different depths and checks how well images match when projected onto those planes. It's a little bit complicated. We will study detail in the next slide. The output of plane sweep stereo is multiview depth maps, right? And the good point of plane sweep stereo is that it is simple and GPU friendly. GPU friendly means we can perform this plane sweep stereo in parallel way without relying much on sequential process. We can utilize parallel computation to the plane sweep stereo, and it is good for dense depth maps. That is the reason why the output of plane sweep stereo is multiview depth maps. But the drawbacks are depth resolution limited by plane sampling and less robust for arbitrary views. And the second advanced approach to multiview stereo is space carving stereo. It divides the 3D space into small blocks, which is called voxels, and gradually removes carves. Gradually removes means carves. Carve is like let's say we have some basic 3D sculpture, and we'd like to change its shape by removing some unnecessary part from the sculpture. That is called carve. So we'd like to carve. That is the reason why we call this algorithm space carving stereo. We gradually remove the blocks that don't look consistent from multiple camera views, leaving the object shapes. So the output is full 3D model. It is different from plane sweep stereo, right? The output of plane sweep stereo is multiview depth maps, but here, space carving stereo, the output is full 3D model. It is different. And the good point of space carving stereo is it produces full 3D volume. It is a good point. So, I mean, the plane sweep stereo, it outputs only multiview depth maps. Multiview depth map is not full 3D volume. I mean, depth map is, I introduced this in previous class. Depth map is a 2D, 2.5D representation. So it has height and width, and each pixel value is a depth value. Pixel value, depth. This is called depth map. Although we have multiple depth maps, it is not full 3D. I mean, depth map, for example, for each depth map, it only have depth values of visible vertex, visible points. It does not have information of invisible points. So it is not, multiple depth map is not a full 3D volume. And the output of space carving stereo is full 3D volume, flexible for arbitrary viewpoints, enforces consistency, but the drawback is it's computationally heavy, and this accurate calibration sensitive to noise. So there are two advanced approaches to multiview stereo. The first one is plane sweep stereo, whose output is multiview depth maps, and the second approach is a space carving stereo, whose output is full 3D model. We will study this one by one. The first one is plane sweep stereo, first advanced multiview stereo algorithm. This is a pseudocode of plane sweep stereo. Plane sweep stereo looks a little bit complicated, but I think this pseudocode is very clear and shows what is happening in plane sweep stereo. So there are two loops, right? Outer loop and inner loop. For each reference view, let's say we have multiple images. Image 1, image 2, image 3. So at the first iteration, we call this reference. Next, we call this reference. Next, we call this reference. So this is outer loop. And for each depth plane, once we select, let's say we select a second image as a reference view, then for each depth plane, we create a depth plane, virtual depth plane, and then project all neighbor views. Let's say our reference view is I2, then neighbor view are I1 and I3. This is reference, this is neighbor, this is neighbor. To candidate plane. So candidate plane means, so let me draw this again. So this is I1, this is neighbor, this is I2, this is reference, this is I3 neighbor, and I2 is reference. So we can construct multiple planes like this: plane 1, plane 2, plane 3. So we project all neighbor views. We project I1 and I3 to P1 and P1, P2, P3. We project this. Compare the projected image to reference image. We project I1 to P1, and we compare the projected I1, which is on the P1, and our I2. We keep repeat this, and then we get optimal depths of reference image, because this is in this loop, right? This getting that optimal depth map is inside of outer loop, right? But the optimal depth is just the depth of reference view, right? Minimal error for each pixel. So for each reference view, it constructs some virtual depth plane. We will study detail later. For each reference view, once reference view is selected, we construct virtual depth plane, and then we project all neighbor view images to candidate plane, which is a virtual plane, and then compare the projected image to the reference image. And we keep repeat this for all depth plane, for all virtual plane, and then we get optimal depths of reference image with minimal errors for each pixel. And we keep repeat this, then finally we can get depth maps of all images. That becomes multi-view depth maps. Here we introduce, we studied that the output of plane sweep stereo is multi-view depth maps. So that is how we get multiple depth maps from multiple images. Let's see detail. So this is a 3D object. And let's say we have image 1, image 2, image 3. And this shows a good case. Proposed point at correct depths. It is consistent, right? So if this is in the, let's say this is in the virtual plane P1, and we project this green point to the P1, and then we compare this projected green P1 and the point on the reference image. We compare circle and triangle, compare circle and triangle, right? And this one again, I3 again, we lift this one to the 3D space, and then reproject it to the reference view, and then compare it. So we'd like to compare circle and triangle. And here is a good case. The error between circle and triangle is almost zero, right? It looks almost the same. That means this is a correct depth. This point has correct depth, right? So that we can get depth value of this pixel, of this triangle pixel, right? The depth value of this point is correct, so that we can properly get depth value of this triangle pixel. But the failure case is, the bad case. This is the incorrect depth. So let's say this is a triangle, but this is circle. This circle, and it is projected to the reference image viewpoint. that becomes this one. And the pixel value, here is just the white, right? White, and here, this is just white pixel. Just background pixel. And this is just some bluish pixel, right? Blue pixel. So we also compare circle and triangle. And it turns out that circle and triangle are very different. So we can say that the lifted and reprojected point, which is circle, and the reference image viewpoint, triangle, is very different, so that they have huge consistency distance, so that we can conclude that this point has incorrect depth. If it has correct depth, then as this slide shows, the distance between circle and triangle should be very small. But here, distance between circle and triangle is very large, so that means this point has incorrect depth. So we need to change we need to change something. We need to change the plane. We need to change to get correct depth. So we sweep family of planes parallel to the reference camera image plane. Here are P1, P2, P3. We sweep family of planes parallel to the reference image plane. This is reference image, right? And reproject neighbors. This is neighbor camera 1, neighbor camera 2, neighbors onto each plane, and compare reprojections. We lift this neighbor camera to the 3D space, and then project again to the P1, project again to P2, project again to P3, and then we compare projected image and reference image to measure consistency distance. As this slide shows, if consistency distance is small, then the depth value of this point is correct. If consistency distance between this circle and triangle is very huge, then depth value of this point is incorrect. We can conclude that. This shows an example. For a particular depth sweep, some regions in the average image appear sharp, photoconsistent. So there are many blurry and some of pixels are sharp. For example, this is relatively sharper than this region, right? So that we can say that depth value of this region is more accurate than this region. This is just the average of reference image and reprojected images. So as I said, this is still, keep it very consistent with the previous slide. If the distance between I2 3D R. This is the consistency that we are interested in. We lift I2, no, here, sorry, no I2, I1. We lift I1, this is I1, right? Image 1 to 3D space, and then project again to reference image, which is I2. We can rewrite this. Distance I1, 3D, I2, right? We can lift neighbor image to 3D space, and then project it again to the reference image, which is I2, and then we can compare this reprojected one and then I2. If the distance between, pixel distance or any similarity between reprojected I2 and original I2 is very small, if similarity is very large, then we can say that those two are consistent, so that we can conclude that those points have correct depths. If distance between this reprojected one and original data is far, distance is very long, then we can conclude that they have incorrect depths. This is also the same. If distance between reprojected one and original image is very small, then although we perform averaging, the image should look sharp. Image should look sharp, right? But if the distance between reprojected one and original image is very long, then averaging them out will give very blurry result like this. So this sentence shows that for particular depth sweep, some region in the average image appears sharp. Appears sharp means photo consistent, because distance between reprojected one and original data is very small, so that although we perform averaging, they look consistent, they look sharp. But if distance between reprojected and original pixel is very long, then they produce blurry averaged visualization, right? So this shows so we can so in the inner loop, right? We construct some virtual depth plane. We can construct here we constructed P1, P2, P3, right? We can still keep construct P4. We can construct P5. We can, but we cannot infinitely construct virtual planes. So we start with near depths till far depths. So we have some threshold. We have some threshold, minimal depths and maximum depths, and then we construct planes in the range of minimal depths and maximum depths. And here is a cost volume. Cost volume means, so in the inner loop, for each reference view, let's say we have inner loop, we can construct multiple planes, right? P1, P2, P3, P4, P5, and then for each depth plane, we reproject neighbor images to those planes, and then compute and compare the projected image to reference image, right? And then we can, for each plane, we can then store similarity between reference image and projected image, right? In P1, we can compare similarity of I1, 3D, I2, P1. This is P1. This is, and the second one, similarity I1, 3D, I2, 2, I2. This is P2. We can construct this similarity plane, right? This set of the combination of concatenation of this similarity plane is called cost volume. So cost volume has a 3D tensor, right, with height depth, where D is a depth proposal. So for each depth plane, here we have for each depth plane, we construct this similarity. We save these similarity values on each depth plane, and then we can just make them up and then make them volume. That becomes cost volume. So this means there are D number of planes, right? So the W, H, D. So let's say we so there are D number of planes, right? Each plane has a width times height shape. This one is from P1, this one is from P2, this one is from PD, where P1, P2, PD are like this. We can construct multiple depth planes, and then we can construct similarity from each plane. That becomes each plane in cost volume. So that so CUVD indicates photo consistency between UV pixels in the reference image to that of corresponding pixels in its neighbor image, right? That is what I said. We lift the neighbor images to the 3D space and then reproject it to reference image plane, depth plane, and then compute just the pixel distance for each pixel. And CUVD indicate photo consistency between UV pixel in the reference image to that of its corresponding pixel in neighbor image, right? Assuming depth proposal at D. This means that if C is high, if photo consistency is high at a UV pixel, that means that depth value might be correct at UV pixel. If photo consistency at UV is very small, then it's very likely that depth value is wrong, right? So that means cost volume, just a similarity of all depth plane. And there are measures of photo consistency. A simple one is variance. How do you find the corresponding pixels in neighbor images? Back project every pixel using camera metrics that is computationally expensive. So we can do parallel computation. We can just do a homographic transformation over the whole image, right? So this is just a 2D to 3D and 3D to 2D. It's just a homographic transformation. We learn homographic transformation, right? We know homographic transformation in 3D is just a 4x4 general matrix. Then we can apply in a parallel way. We can apply this homographic transformation for all points in a parallel way over the whole image. So that instead of doing this kind of sequential process, this is sequential process. This is parallel process. So we can do try the parallel computation to make it faster, and which means it's GPU friendly. So for each depth plane, proposal DM, map each target image IK to the reference image IREF using homography. Let the warp image be WKM. K is from target image, M is from plane proposal. And HKM can be calculated from the camera parameters and depths of the plane DM. And for each pixel UV in the reference image, compute similarity score between WKM and IREF. If you use zero mean normalized cross correlation, which is Z and CC, we can have Z and CC, right? So this is exactly the same that as I told you. Let's say we have this, and this pseudocode, I think this pseudocode is very clear and shows what is exactly happening in plane sweep stereo. For each reference image, we pick a single reference image, and then for each depth plane, we construct this kind of P1, P2, P3 virtual plane, and then we project all neighbor view images to the candidate plane, and then compare projected image to reference image. This just and this DNCC shows this kind of process. We lift the neighbor images to 3D space and then reproject it to reference image. That is exactly the same as applying this homographic transformation, HKM inverse. And then we compute similarity using ZNCC. And for each pixel UV in the reference image, compute similarity score between WKM and IREF. Create the cost volume for K target images. The greedy solution to get depth map is that at each pixel, choose the maximum of the cost volume as the correct depth. That is the greedy approach. I guess you learned greedy algorithm in algorithm class. So in cost volume, it has similarity, right? It has similarity. So for each depth, it has height, width, d, right? And for each position U, V, D, we can access to the similarity between reprojected and referenced image, and then we can just perform argmax. We can perform argmax to get D value, and that becomes depth value of that pixel point position UV, right? Non-greedy approach, we can use advanced techniques like belief propagation, graph cut, or 3D convolution. We're not going to study this kind of non-greedy approach detail. You can just understand why we can try greedy approach and what greedy approach mean. Let's say we have a cost volume, then we can just at pixel we can choose maximum of the cost volume as the correct depth. We can just perform argmax to get correct depth value. That is the greedy approach. And this shows what happens if we have wrong depths in plane sweep stereo. But so the top one is just the measurement, and these are reprojected. Measurement means it captures images with camera, and this is reference image, and we take the same 3D object with the left camera and right camera. This gives us left neighbor and right neighbor respectively. And this one, left neighbor projected into reference image. I mean, compared to this one, compared to left neighbor, this looks a little bit different, right? This one also, compared to right neighbor, this one looks a little bit different. It is more likely rotated. Overall image is rotated to the reference image, right? The reason for that is that we leave the left neighbor or right neighbor to 3D space and then reproject the 3D image to the reference image space. Assuming we have good camera parameters from camera calibration or epipolar geometry, then we can transform, we can warp this kind of left and right neighbor images to reference image space. That is, so we can just apply homography transformation, right? But it looks a little bit different from, ideally, this reference image and right neighbor projected into reference image, this one and this one, should be almost the same, ideally. Ideally, reference image and left neighbor projected into reference image, or a reference image and right neighbor of projected into reference image should be almost the same ideally. But unfortunately, you can see clear difference. There is a space, but there is no space. There is no such kind of white stuff, but here so there is some white stuff. That is a little bit different. So the reason is that we got wrong depths. That is the reason. If we get a correct depth, then this one and reference image should be the same. This one and reference image should be the same. But the reason why they look different is that we got wrong depths in plane sweep stereo. Anyway, this is a overall description of plane sweep stereo. Let me just briefly summarize plane sweep stereo. This pseudocode shows the plane sweep stereo. There are two loops, outer loop and inner loop. Outer loop, we iterate for each reference view. Let's say we have all with 3 images, then each image becomes reference image. And for each reference image, we construct depth plane, virtual depth plane. And we project all neighbor views to candidate plane, and then compare the projected images to reference image. And then if distance between reprojected image, this one, reprojected image and reference image distance is small, then we can conclude that depth value of that point is correct. If the distance between reprojected one and original one is long, distance is large, then we can conclude that depth value of that point is wrong. We need to try another depth plane. And these are just visualization and analysis. And cost volume, as I said, cost volume is a 3D tensor, and then it just save similarity for all pixels for each depth value. And let's say we have a cost volume, then at each pixel we can choose the maximum of the cost volume as the correct depth. So we can perform argmax in the depth axis to get depth map. That is a 3D approach. And then let's proceed to another advanced multiview stereo algorithm, which is called space carving. Space carving is very different from plane sweep stereo. Discretized scene volume, and these are input images calibrated. Assign RGB values to voxels in V, photo consistent with images. We haven't learned voxel, we haven't learned volume, but you can easily think like, I guess you're familiar with video game called Minecraft or Lego. All the things, let's say this is human, all the things are just this kind of rectangular shape. And this is volume. Some 3D space which consists of voxel, volume is like a cubic shape is a volume, and each unit, small unit in volume is called voxel. This is called voxel. As we image is plane, right? Plane. And each one is pixel. Volume is a 3D space, and we call this voxel. Pixel, voxel. Plane, pixel, volume, voxel. Anyway, you assign RGB values to voxels in V. We will study lots of 3D representations after midterm, like a volume, point cloud, mesh, implicit, all the stuff we will learn later. But you can, at this moment, you can just be familiar with volume. And this is space carving algorithm. First, we need to do initialization. This is initialization. Define a large bounding volume, voxel grid that is guaranteed to be bigger than the object or scene of interest. At first, we do not know exact 3D shape, right? We do not know exact 3D shape of some object. So let we just begin with some large bounding volume. Bounding volume is like this kind of cubic shape volume that is guaranteed to be bigger than object or scene of interest. And we keep repeat this. For each voxel, typically starting from the boundary and moving inward, project the voxel into all images where it should be visible, and check photo consistency across those images. Compare color or texture. If the volume is not photo consistent, remove it from the volume. Continue this process for all voxels until normal inconsistent voxels remain. So this is very different from plane sweep stereo, right? Plane sweep stereo, we lift pixels to 3D space and reproject the reference image space and then compare the photo consistency. So we start with 2D, plane sweep, sweep, MVS, 2D, 3D, 2D. But space carving, 3D, 2D. It begins with some 3D structure, just a bounding volume, some cubic shape bounding volume. And then we keep remove some unnecessary voxel, where the unnecessary is determined based on photo consistency. We project voxel into all input images where it should be visible and check photo consistency across those images. If photo consistency is small, then we just remove that voxel. We consider that voxel is empty. If the voxel is not photo consistent, remove it from the volume. Continue this process for all voxels until normal inconsistent voxels remain. That is space carving. So space is just a space, right? And carving means, let's say we have some this kind of bounding volume, and then we can just we remove some small element voxel. We just keep element, remove some unnecessary thing from the original huge stuff. That is called carving. We're making some sculpture. We do carving, and this is space carving. It is very different. Plane sweep multi-view stereo. It starts with 2D images, and then we lift them to 3D space, and then we may reproject them, lift the 3D data to the reference image space, and then we compare the photo consistency. But space carving, it starts with the 3D. We have a bounding volume, and then start with the 3D bounding volume, and then we project that each voxel to all the 2D images, and then compare photo consistency to check whether that is empty or not. That is space carving. And these are result of space carving. As I told you, the output of space carving is full 3D model, not multiple depth maps, right? But that is the reason why we can get this kind of full 3D model. Out of 445 images, this is the 3D reconstruction result. And here as well, out of 100 images, using 100 images, we can do 3D reconstruction, space carving, like this. Of course, for the initialization of space carving, as I introduced you in here, you can define large bounding volume, right? Assuming that volume is bigger than object or scene of our interest. But more smart way to initialize the voxel is visual hole extraction. It's very simple. Just a segment out object from background. We have multiple 2D images, right? Then we can segment out object from background using some off-the-shelf algorithm. And then we can back project each silhouette to 3D space and then intersect back projected volumes. That makes some rough 3D shape of our interest. Of course, this does not give a perfect solution because inside of mask just filled with one. This is binary mask, right? There is no information, so it might give some very smooth, some very coarse 3D geometry, but it can be very useful for initialization of the space carving. So here, there's summary of approach to MVS, plane sweep depth maps, robust and adaptable multiple view stereo matching, real-time applications, fusion of point cloud from different reference views, sampling of scene depth depends on the reference views. So let's check one by one. Robust adaptable multi-view stereo matching and real-time application because it's GPU friendly. Fusion of point cloud from different reference views, right? We and for each iteration we choose different reference image, and for each reference image we project. We lift the neighbor images to 3D space and then reproject them to the reference image space. And sampling of scene depends on the reference views, right? But the volumetric stereo is a space carving. View independent representation, right? Because in these plane sweep depth maps, we change it reference image, right? But here there's no reference image, just the full 3D stuff. View independent representation needs silhouette extraction for the initialization. We use visual whole, right? Visual whole extraction for the initialization. Accuracy depends on the density of the grid and high computation and memory cost. And let's finalize with the converting depth to mesh. For the space carving, there's no problem. The output of space carving is 3D model, so we can just use that as it is. But the output of plane sweep stereo, the output is multi-view depth maps. So we need to change multi-view depth maps to mesh. But the depth map, the point cloud is straightforward. We have all kinds of information. We have camera parameter, we have image coordinate, we have depths, so that we can lift them to the 3D space. There's no problem like this. So here, right? And using this one, we can lift point depth map to the point cloud in world coordinate system. There's no problem. All camera different coordinate system, different rotation translation. So this extrinsic is different for each camera. Anyway, if we try extrinsic of each camera, then we can lift the depth map to the point cloud. It's straightforward, right? And we will not study detailed, but one of the most popular way to convert the point cloud to mesh is a Poisson surface reconstruction. How do you obtain mesh from point cloud? We can use Poisson surface reconstruction. That is one of the most popular algorithm people keep using even these days. So this is the end of multi-view stereo. So far, midterm will cover all the stuff until this multi-view stereo from lecture 1 to lecture 9. And you need to fully understand pros and cons of each algorithm. In some situation, which algorithm, which pipeline should be used, what is the ambiguity of such system, and how can we resolve such ambiguity. You need to be fully familiar with such kind of challenges for the midterm. So let's finish. Thank you.